All right, so we're going to reach the halfway point with the cardiopulmonary unit by talking about oxygen and carbon dioxide transport. A fair amount of this should be review, but it's good review nonetheless. And it'll help with things that we talk about later on this week and next week. So oxygen transport, we've got 3 or 4 things, and carbon dioxide transport, we've got a couple of things. Okay, so if you recall, the main ways that we transport oxygen are when it's bound to hemoglobin and when it's dissolved in plasma. And as you can see, an overwhelming majority is bound to hemoglobin. That's the important one. Okay, now the relationship between the partial pressure of oxygen and the saturation of oxygen is shown by the oxyhemoglobin curve. Now there's a couple things that I want you to remember here. Okay, this is a measure of what's in the plasma. And then this is what's a measure of what's in the hemoglobin. That's a very long G. Okay. Now, we don't have a saturation sensor that we're aware of. Okay, but we do have pressure sensors, and so it's really important to know this relationship. And so it's really interesting that when we get about here. Okay, when partial pressure drops to about 60, which is equivalent around 80, 85, depending on a whole bunch of factors, that's when the chemoreceptors, peripheral chemoreceptors especially, start to go nuts with their firing rate. Because they're indicating to the brain that, hey, when pressure starts to drop below 60, saturation is going to tank. Okay. Now, as you can see, we've got the curve can shift left or it can shift right, and there's an effect of each of those. All right, so a left shift, this occurs due to decreased acidity, temperature, and or carbon dioxide, pressure of carbon dioxide. So this is the cause, this is the effect, and the effect is it makes it easier for oxygen and hemoglobin to get together. And this should make sense because acidity is really a measure of hydrogen ion. So just think of hydrogen ion and carbon dioxide as molecules that can take the seat on hemoglobin for oxygen. If those seats are filled with other things, oxygen can't bind. Okay, and so if we get rid of these molecules, there's available seats, and so it's easier for oxygen and hemoglobin to get together. All right. On the flip side, we've got a right shift. And the opposite is true. If I increase acidity or increase temperature or increase carbon dioxide, that's going to reduce or decrease the affinity between oxygen and hemoglobin. Okay, that's going to facilitate unloading. What's really interesting is if you think about it, in the lungs, we have relatively low temperature, low acidity, low CO2. In the tissues, we have high temperature, high CO2, high hydrogen ion, especially during exercise. And so the way things work, in my lungs, I've got an environment that naturally occurs that facilitates loading of oxygen, whereas in my tissues, I've got an environment that facilitates the unloading of oxygen. Now, we can have a Bohr or the Haldane effect. And so the Bohr effect is that if I've got more CO2, I've got less affinity or less attraction between hemoglobin and between hemoglobin and oxygen. This occurs in the tissues, like I just said. The Haldane effect is that if I have high oxygen, that reduces the affinity between hemoglobin and carbon dioxide. This occurs in the lungs. Okay, so this is essentially what I said on the last slide, but now these guys are fortunate enough because they've discovered this or understood this that they get their name put on it. Now, next is something called oxygen carrying capacity. Okay, and so when you hear about a plane or a vehicle of some sort, it always talks about capacity. Okay, and so capacity is just kind of like what's the max that this can hold, whether it's in terms of people or just actual storage space, that sort of thing. And so in order to determine the oxygen carrying capacity, there's 3 things that we need to know: the hemoglobin concentration, the saturation of oxygen, and the partial pressure of oxygen. And so we can calculate capacity by using the following equation. Okay, 1.34 milliliters of oxygen per gram of hemoglobin times the hemoglobin concentration times saturation plus 0.003 times the pressure of oxygen. Okay, now this number here is a constant. This number can vary, so depending on what's going on. So women are going to have a lower hemoglobin usually. And then the partial pressure, just depending on where you're at. All right, but saturation, when I'm calculating capacity, will always be 100%. Okay, so if I want to know capacity, I always set saturation 100%. That's the max. Okay, and so in this case, our maximum oxygen carrying capacity would be 20.4 mils of oxygen per deciliter of blood. Okay, or in other words, 1/10 of a liter. Now, if I want to know actual oxygen content, I use the exact same equation. The only thing that's different is saturation. Okay, and so in this case, let's just say that I set my saturation, or my saturation is 98%. This goes from 20.1 to 19.7. Okay, that's not going to change, that 0.3, and so our oxygen content is 20 milliliters of oxygen per deciliter of blood. It's important to know that hemoglobin concentration is lower in women, lower in people with sickle cell, but for the most part, that's not a big deal. However, during intense aerobic activity, intense exercise, this can be a big deal. All right, as any of the student athletes know, one of the things they have to do as a freshman is they have to take a sickle cell test just to make sure they don't have sickle cell, because they want to make sure that there aren't going to be any issues with that. So once we know content, though, we can calculate delivery. Okay, and so delivery is just oxygen content times cardiac output. And so just to make the math nice and easy, we're going to say that we've got 20 milliliters of oxygen per deciliter of blood. And let's say that our cardiac output at rest is 5 liters of blood per minute. Okay, well, we've got to get these into the appropriate units. And so to convert deciliters into liters, there's 10 deciliters in a liter, so we go 20 times 10. So now we've got 200 mils of oxygen per liter of blood times 5 liters of blood per minute. That gives us 1,000 mils of oxygen per minute, or in other words, 1 liter of oxygen per minute is being delivered. Okay, now let's say that we increase that to, let's say that our cardiac output's 25 liters a minute. Well, then our oxygen delivery would be 5 liters. Okay, so that's oxygen. On the other side, we've got carbon dioxide transport. Most of our carbon dioxide is converted to bicarbonate, where it's transported in the plasma as bicarbonate. Some remains dissolved in plasma just as CO2, and then a small percentage also bound to hemoglobin. Now we've got this equation that hopefully you've all seen before. And so if we go through this, we've got carbon dioxide plus water. With the help of carbonic anhydrase, we'll create carbonic acid. It's one of the things that's in your soda. And then that carbonic acid can break into hydrogen ion and bicarbonate. Now, this is an equation that can go either way. That's why we've got the arrow pointing both ways. And so what happens is, in the tissues, this equation shifts to the right because we transport CO2 as bicarbonate. We don't want CO2 on the hemoglobin, or we want to reduce or limit the amount so we can carry oxygen. So by shifting it to the right, we reduce the amount of CO2 that's bound to hemoglobin. But once we get to the lungs, everything reverses, and we're able to convert bicarbonate into carbon dioxide, and then it diffuses into the alveoli, and we exhale it. Okay. It's also important to note that, and this will be important, I think, during week 10, that this relationship is important because CO2, we can alter how much CO2 is in our bloodstream, and therefore how much hydrogen ions in our bloodstream with our ventilation. Okay, CO2 is an acid, bicarb is alkaline, and so if we have high blood pH, which means we've got we're alkaline, we're going to shift the equation towards CO2. We're going to create more CO2, which makes us more acidic. But if we're really acidic, then we'll shift the equation this way, so we're creating more bicarb. Okay, and this will be tied into something called ventilatory threshold that will be coming up next week.